this sequence of videos, we're going to cover polynomial factorization and the concept of irreducible and reducible polynomials. So let's begin. We've had this definition before somewhere in previous slide or in homeworks, but let's give the definition to start out on the right foot here. Let's define what it means to be an irreducible polynomial. Now, what's interesting is that the definition of an irreducible polynomial depends on the field over which you're working. So let's first introduce what we're doing here. In the polynomial ring f adjoined x, where we're focusing on the case where f must be a field, then a polynomial little f is said to be irreducible over the field f, capital F, if it has positive degree and it cannot be factored in the polynomial ring you're working in into two positive degree polynomials. So let's give some examples here to understand this definition a little bit further. According to this definition, all linear polynomials in f adjoined x are irreducible. Doesn't matter what the field is, just if you have a linear polynomial, it's automatically irreducible over that field. The reason is this: a linear polynomial has degree 1, so it has a positive degree, and there's no way that you can factor it into two positive degree polynomials. If you have two positive degree polynomials and you multiply them together, each of them has degree at least 1. Their product will have something degree 2 or higher. So anything that's a linear polynomial can only factor as one of the two things being a degree 0 polynomial. That's a non-negative degree, so that doesn't count. Second, and this is a good example because in our definition, we talked about what it meant for a polynomial to be irreducible over a particular field. I want to stress that what the field is important. You can have polynomials that are irreducible over some fields, but not irreducible over others. And so I want to give a couple examples to demonstrate that. The first is the polynomial x squared minus 3. If we think about this polynomial as living in the polynomial ring Q adjoined x, so the coefficients on the polynomial x squared minus 3 are rational numbers. In fact, they're integers, but we're requiring our field to be a field. So rational numbers are a field. All the coefficients on x squared minus 3 are rational. It is not possible to factor x squared minus 3 as a product of polynomials that have rational coefficients, and therefore the polynomial x squared minus 3 is irreducible over the rational numbers. However, we can factor x squared minus 3 as the quantity x plus the square root of 3 times the quantity x minus the square root of 3. And the numbers square root of 3 and negative square root of 3, those are real numbers. So we can factor x squared minus 3 as the product of two positive degree polynomials in R adjoined x, but we cannot do so in Q adjoined x because root 3 and the square root of 3 are irrational numbers. Similarly, I wanted to do another example where we just change the fields to be something slightly less familiar than the rationals or the real numbers. But the polynomial x cubed plus 2x plus 1 is irreducible over z mod 3. That's something that's fairly straightforward to check that I will show you a little bit later. However, this polynomial happens to be reducible over z mod 11 since 9 is a root modulo 11. That is, if you looked at 9 cubed plus 18 plus 1, you'd find out that that number is divisible by 11. So 9 happens to be a root of this polynomial. According to our slides from last time, we know that that means we can factor out an x minus 9 from x cubed plus 2x plus 1. When we do that and reduce everything modulo 11, that x minus 9 turns into an x plus 2, since negative 9 and positive 2 are the same modulo 11, and the remaining factor turns out to be x squared plus 6x plus 9. Now, each of these polynomials, x plus 2 and x squared plus 6x plus 9, happen to be irreducible in z mod 11. So we started with a polynomial that happened to be reducible over z mod 11, and we've written it as a product of irreducible polynomials. All right, let's continue by working in the ring R which is f adjoined x. We want f to be a field. That's what we'll be focusing on these days. And let's start by examining a polynomial, little f, inside of the ring R. What we're interested in is figuring out if f is an irreducible polynomial, or figuring out if f factors into polynomials of smaller degree. Really, this should be the point where you're in an abstract algebra class and it actually reminds you of the algebra class you took in high school. I know that when I was taking algebra classes, I did a 24-page packet on taking polynomials and factoring them, which is really what we're doing in this lesson. We're just not necessarily working over the real numbers anymore. And this is the big question. This is the question that algebraists are interested in. I take a polynomial, when does it factor, when does it not? One approach to tackling a big problem like this is to start with the smallest, easiest examples that we can while trying to keep the field f arbitrary. So let's start with that. Let's take a polynomial f, and let's start with the smallest examples we can come up with. Let's take a look at linear polynomials. And what I'm really going to be discussing on this slide is the relationship between the reducibility of a polynomial, if it factors or not, with does it happen to have a root in this ground field f. Now, if you start out with a polynomial in f adjoined x, and it happens to be linear, that is, it has degree 1, then that polynomial automatically has a root in the ground field f. For this, we're going to need to use the fact that f is a field. And I haven't provided a written justification, but let me get you started. I think you should prove this as an exercise to yourself or look it up in Galleon. I think the key thing here is to reduce even one step further to make this problem really ridiculously easy. So let's say that we start with a linear polynomial, ax plus b, and let's assume further that this linear polynomial is monic, meaning that that coefficient a in the ax plus b happens to just be the unit of the field, so it's just 1. So really what we're saying is, if I have the polynomial x plus b, does it have a root in the ground field f? Well, we know that this polynomial x plus b has a root when it's equal to 0, and if we have x plus b is equal to 0, and we move things around in that equation, we solve for x and see that x is just the additive inverse of b. Because b belonged to the field, and it is a field, the additive inverse also belongs to the field, and so that's your root, the additive inverse of the constant term. Now what I'm leaving to you as the exercise is to go back and remove that assumption that I made that the leading coefficient in ax plus b, the a is equal to 1. Now start with the a actually being there, being present, and see if you can prove the same thing, that ax plus b has a root in the ground field f. What I'd rather do is really focus on justifying the next statement. So once we've understood the linear case, f is some sort of linear polynomial, it automatically has a root in the ground field. Let's go up to something of degree 2. And in fact, the same argument for degree 2 will work for degree 3, so we can kind of kill two birds with one stone here. If our polynomial has degree 2 or 3, then the following is true, which is very useful. The polynomial f, little f, is reducible over the field capital F if and only if little f has a root in f. Now this is an if and only if statement, so we have to prove two things. The first thing we have to do, the first thing we will do is assume that little f has a root in the ground field f, and then we will show that the polynomial is reducible. This is really something we've already done. In our collection of slides from last time, we showed that if f has a root in the field, then we know that x minus that root divides the polynomial, and we can write that polynomial as x minus the root times something else. And that's what it means for a polynomial to be reducible. I wrote it as x minus the root times something that has positive degree. So that direction is easy. That's something that we covered in the last slide. So let's do the converse now. Let's suppose, conversely, that we can take the polynomial f and we can factor it as g of x times h of x. And not just factor it, it's got this non-trivial factorization. The degree of g of x and the degree of h of x each is at least 1. Right? Neither of them has degree 0. Now think about this. Let's think about the degrees of g and h. We know that they're at least 1. What happens if both of them had degree 2 or higher? from the way that we know how to multiply polynomials together, we know that the degree of the leading coefficient in their product is going to be the sum of the degrees of the leading coefficients in each of g and h. In other words, we're doing kind of a specific example. If g and h each had degree 2, then their product, g times h, would have degree 4, 2 plus 2. And that's going to be too big because we're assuming that the degree of f is 2 or 3. So we know that g of x and h of x, they each have degree at least 1, but one of them, either g or h, must have degree at most 1, or else you're going to get a product, f, whose degree is too high. That means that one of g or h is a linear polynomial. It has degree 1. And this linear term automatically has a root in the field by the first statement that we made. So that finishes the justification here. Again, if you find these arguments confusing, we're working over an arbitrary field f, but really try to think back to your high school classes where you worked on factoring polynomials and just work a handful of examples in the familiar case that is like high school algebra to you, and some of these things should still make sense, or make a little bit more sense if you think about those specific examples. Now, where this is really helpful, this particular statement, if f of x is a polynomial of degree 2 or 3, then f is reducible over the field if and only if it has a root in the field. This can be really useful when you're working over a finite field, because what it means is if I give you a polynomial and it has degree 2 or 3, in a finite field, all I need to do is just run through the elements of that finite field and check to see if any one of them makes the polynomial 0 when I plug them in. If it does, then you automatically have a reducible polynomial. If it doesn't, then your polynomial is irreducible. And so this is, again, really helpful when you have a finite field. To make that point really clear, I want to go back to the example that I had on the previous slide. So let me remind you what that example was, and I want to show you how to apply this. So here's the example I had, the polynomial x cubed plus 2x plus 1. I said it's irreducible over z mod 3, but that it was reducible over z mod 11. How did I know that? Well, I started with this polynomial, and what I did is I just tested out some elements. So over z mod 3, I said it's irreducible. This is a cubic polynomial. All I had to do to check that it was irreducible was check that if I plug in 0, 1, or 2 for x, respectively, in this equation, that I was never getting 0. 0 plus 2 times 0 plus 1 is 1, that's not 0. 1 plus 2 plus 1 is 4, mod 3, that's 1. Then 2 cubed is 8, plus 4 is 12, plus 1 is 13, and mod 11, sorry, not mod 11. Now I've forgotten what I've done. 2 cubed, 8, 4, 13, modulo 3, that's 1. It's not 0. Therefore, I checked 0, I checked 1, I checked 2 with some difficulty, but I was able to see that I never got 0 when I plugged them in, and that's the proof that this polynomial is irreducible. Just as a little bit of a side note, I want to stop here and show you, z mod 11 is a little bit more annoying. Modding out by 3 was difficult enough for me in this slide to do off the top of my head, so modding by 11 is something I trust myself with even less, and there are 10 things I'm going to have to, or 11 things that I'm going to have to check here. I'm going to have to check the numbers 0 through 10. So what I could do if I really wanted to, which could be a good help to you when you're working through these homework problems, is I could use Excel. So let me show you how I did that. Remember, my polynomial is x cubed plus 2x plus 1. Let's pull up Excel. And what I'm going to do is down this column, I'm going to put the numbers that live in z mod 11. And in this column, I'm going to put a formula. I'm going to set this equal to the cube of this cell plus 2 times the quantity in this cell plus 1. Works out at least for 0. That one's easy enough to check. And then what I'm going to do is I'm going to drag down on this cell to copy that formula. So you can see that, for instance, when I'm looking at this 136 cell, what I've done is I've taken the cell in A6, that 5, and I've multiplied by itself 3 times, Then I've added on 2 times the value in that cell, and then I've added on the constant, which is 1. And I've done that for each of these values modulo 11. The last thing I could do is Excel knows how to do modular arithmetic, so I go to the cell over and I hit equals mod is the command for modular arithmetic, and I'm going to put mod the cell to my left, and what do I want to mod by? I want to mod that number by 11. So here's the outright answer, and then in this column I'm going to put the answer mod 11. With this 0, 1, and 1 it's not very interesting. 1 is itself modulo 11. The same will be true of 4. When I do the 13 I should get that 2 there. And you see that I do. So it's really and truly doing modular arithmetic. And this is the way that I determined that 9 was a root of that polynomial. I used Excel, and it showed me that when I plugged 9 into that formula, and I took the result modulo 11, that I was getting 0. Okay. End of that little digression. Let's continue on. Make that a little bigger. So this is where we left off. We had started with polynomials of small degree, and we were trying to figure out if they were reducible or not. And at least up to degree 3, we were finding something really convenient. The reducibility of the polynomial was basically the same as if the polynomial had a root or not over the ground field. And so this was making things really easy for us to check. The thing that makes this interesting, and the reason that we study this in an abstract algebra class, is because that's the full story in terms of polynomials of small degree. As soon as you hit 4, trouble starts to arise. That is, if you take a polynomial of degree 4 or larger, then both situations can occur. You're going to lose this if and only if statement. So what do I mean by that? For example, let's take this polynomial f of x, which is x to the 4th plus 2x squared plus 1. That factors as x squared plus 1 times x squared plus 1. That's going to be reducible over z mod 3 because I've written it as the product of x squared plus 1 and x squared plus 1. It's going to be reducible everywhere. However, the polynomial x to the 4th plus 2x squared plus 1 doesn't have any roots in z mod 3. So I have a polynomial, it's definitely reducible, and yet it doesn't have any roots in the ground field. And I need degree 4 or higher for that to be true, but that is a different behavior than we were seeing, even over a finite field, than in the degree 2 or 3 situation. However, of course it can go the other way. If I have g of x to be the polynomial x to the 4th minus 1, that's definitely reducible over z mod 3. 1 is a root of that polynomial. So you do have a root, and it is reducible. But in the previous example, we did not have a root, but it was still reducible. So you can have reducible polynomials, and they need not have a root in that ground field, which I guess is perhaps the more interesting of the two situations. Last in this first slide, this should go real fast, I just want to state a couple of theorems, and then we're going to dive into them a little bit further in the next video. So the first lemma that I want to state is Gauss's lemma. This is a pretty cool lemma. Gauss is a pretty cool dude. And what does his lemma say? It says, suppose you have a polynomial f of x. Now we're going to go back to a familiar field, the rational numbers. And let's suppose that we have a polynomial that happens to have integer coefficients. And suppose we know that it's reducible over the rational numbers. Then in fact, that polynomial is reducible over the integers. What this lemma really means is if I had a polynomial, it had integer coefficients, and I knew I could reduce it over the rational numbers, then I could also reduce it over the integers. The example I'm going to give you is this. I don't have it appearing on the slide because there wasn't any room. But if I had the polynomial 6x squared minus 17x plus 12, that's a polynomial. It's got integer coefficients. And suppose somebody came up to me and gave me the information that I could factor that polynomial. I could factor it as the quantity 3x minus 9 halves times the quantity 2x minus 8 thirds. Each of those is a polynomial, a polynomial with rational coefficients. What's true is I would know automatically that I could also factor 6x squared minus 17x plus 12 as a product of two polynomials where those polynomials had integer coefficients. I could do better than the rational coefficients that I was given. And the factorization of that is the quantity 2x minus 3 times the quantity 3x minus 4. Both of those are factorizations of our polynomial f of x. One of them is just maybe a little bit nicer than the other because all the coefficients happen to be integers. Now what Gauss's lemma is really used for is this theorem that we're going to use a lot, which is a theorem due to Eisenstein. And in fact, I will just call the theorem Eisenstein's criterion. I really mean Eisenstein, not Einstein. Eisenstein was a student of Gauss, and so when you look at the proof of this theorem by Eisenstein, he uses Gauss's lemma to accomplish this. So I wanted to state Gauss's lemma because we're going to need it to prove Eisenstein's theorem. But really the important thing that we're going to use over and over again is Eisenstein's theorem. His theorem says this: suppose you have a polynomial, f of x, and let's write out what that means. It's a sub n x to the n plus dot 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 plus a1 x plus a naught. And let's suppose that that's a polynomial with integer coefficients. Then he came up with some conditions to check if f of x is an irreducible polynomial over the field of rational numbers. We'll say we will be able to use Eisenstein's criterion to show that this polynomial is irreducible, again over the rationals, if we can find a prime number p with the following properties. The prime number does not divide the leading coefficient, but it divides all of the other coefficients. It divides a sub I for all 0 less than or equal to I strictly less than n. So it doesn't divide the leading coefficient, divides all the other coefficients, and then the last criteria is the square of that prime cannot divide the constant term. If you can find a prime that satisfies these three properties for the polynomial, then this polynomial is automatically irreducible over the rational numbers. It's not going to factor into rational numbers. We'll do some examples with this in a minute. This is where this video is going to end. It's the statement of Eisenstein's theorem. You'll notice too that when I named this slide, I said that this was the first of 3, and in parentheses I put 4 videos sort of on this subject. This is what I mean. I would like to do the proof of Eisenstein's theorem. I think it's a really cool proof. It uses all sorts of different techniques in crazy cool ways that we've seen so far in the class, and I just think it's a really nice proof. However, it's a long proof. It's kind of hard, and I wouldn't expect anything of that difficulty out of you in this class. So I'm going to record a video. It's going to talk through the proof of Eisenstein's theorem because it's a really cool proof. But I'm not even requiring that you look over that as part of your study for this collection of slides. If you want to look at it, if you want to try and understand it, it's there. The proof that I'm providing in these slides is different than the proof in Galilean. I like it better, but I'm a little biased. So if you had read Galilean's proof and you were looking for sort of something supplementary or something different, that's another reason you might want to watch that video. Again, choose your own adventure from here. If you want to watch that proof, go ahead. I think it's really neat. I'm going to push you to say, please, please, please try. But it's not necessary. You're not going to be tested on it. So don't stress over it if you start the video and you find it a little intimidating.